Okay, so we have already learned some information about sound. Now we are going to talk about something called Doppler effect. It says here that the Doppler effect is the apparent change in frequency due to the motion of a sound source or the motion of the observer. I want to pause for a moment and talk to you guys about the meaning of the word apparent at the beginning of this sentence. It says that it is an apparent change in frequency, and this word is really important because this does not have the same meaning as if it were to just say a change in frequency. The frequency of the sound that is created is the same all the time. So if we have an object that is emitting a sound, and so I see over here on the right, there is a picture of an ambulance. I always tell my students I use this picture because it is a very common example. I actually do not like the example of an ambulance being our sound source. And the main reason for that is because the siren on the ambulance is actually emitting different frequencies. It intentionally is designed to have different sounds coming from it. So I don't want you to think of this as being an ambulance. So we're just going to cross out ambulance here. I just want you to think of it as being a car, okay? And instead of it having a siren, this is just going to be a car that just makes noise because when the engine is running, it emits a sound. So here we have some object. You can even think of it as a motorcycle, okay? It might be easier to imagine a motorcycle with that low rumbling sound. So we have a vehicle that is going to give off sound. It makes a noise the whole time. Now, the sound that comes from that motorcycle or from that car does not change. But if the car or motorcycle is driving around and you are on the street, maybe you're waiting to cross the street at a stop sign. As that vehicle approaches, as that vehicle drives away, that sound may seem to be different to you. But the car itself, the motorcycle itself, does not give off different sounds. It is one sound coming from that vehicle. So when we say that as the motorcycle approaches at a really high speed, that it has a high-pitched frequency, the motorcycle is giving the same sound off, but how we perceive that sound to be, that's what changes. So when we say the apparent change in frequency, we think, our brain thinks that the frequency has changed. We think that motorcycle makes 2 different sounds or 3 different sounds as it's coming and going. In reality, the motorcycle makes one sound. But because of the motion, because the object is moving, or because the person that's listening is moving, either one, because someone or something is moving, how that sound is perceived by the brain has changed. That's what we mean when we say apparent change in frequency. Now, something or someone has to be moving. If both objects are stationary, then the sound is received in its true form. Okay, the original signal is heard. But if someone or something is moving, and yes, the speed at which they are moving makes a difference. So a lot of times in class I say, if we're running away, or if we're speeding away, or if we're running towards, right? I tried to paint the picture of us moving quickly because that is going to have a larger impact on the changed frequency that we perceive. And so it's a little bit easier to kind of comprehend with the example of something moving or coming very slowly. Very quickly. So we want to try to picture that with a high speed motion. But really, motion in general is Doppler effect. Okay, so here is an illustration of what is happening when we have a moving object. So once again, this is just a vehicle. This is not going to be an ambulance. This is just a vehicle that is moving, and that vehicle creates a sound when it moves. So if you are standing in front of the moving object, how you perceive the sound will be different than if you are standing behind the same moving object. Now, in general, if this car is going to emit a sound, sound travels in all directions. So waves in general travel in all directions. So if this object is emitting a sound, what they're trying to illustrate here with the circles is that the sound is traveling outward in all directions. Okay. So if the object is stationary, if we are not moving, then these sound waves are going to be emitted so that they are evenly spaced out. But if my object were to emit a sound wave and then move towards that wave, when it emits the next sound, the waves are going to be closer together because this object has moved in that direction, so that is going to cause the next wave to be emitted at a shorter distance from the first. And so that's what we see over here. The front of the moving object, you see your waves are squished together because of the logic of I emit a wave and then I move towards it, so the next wave is closer. And so people who are in front of our moving object are going to receive a pattern that has the waves closer together. So higher frequency means that we are going to perceive this sound to be high pitch. Remember, the frequency of the wave determines the pitch. The opposite effect happens on the other side. If we emit a wave and then, so here's my object, if it emits a wave and then the object moves away from that sound wave. So we're going to take this guy and we're going to move him away. So now whenever he emits the next sound, there is more space between these waves compared to the original. So originally they are spaced like this, and then with it moving away, you can see there is more space between them. So if you are the person over here, you are going to receive this signal, which has the waves spread out more. So it reaches your ear with a lower frequency, and so your brain is going to perceive that to be a lower pitch sound. If you are in front of the wave, once again, here is the original spacing. But if my object moves towards that initial sound wave, you see there is less space between them. And so this is why the circles around our moving object in the original picture are squished on one side and farther away on the other, okay? All right, on my website, I have a couple of different videos. So if you are familiar with the Big Bang Theory TV show, Sheldon Cooper dresses up as the Doppler Effect for a Halloween costume party. And so there are a couple of videos on my site that are over Doppler Effect. So if you can see over here in the bottom right-hand corner, I have the Big Bang Theory Doppler Effect montage. That is on the site. And then I also have this second video, which I currently have pulled up on the screen, the Doppler Effect, What Does Motion Do to Waves?
The Doppler
and so
Effect.
This video is going to show
In
you a little bit
Sheldon's
of the
words,
clip.
It's the apparent change in the
Sheldon
frequency
Cooper
of a wave caused by
and,
relative motion
the
between
Big
the source
Bang
of the wave and the
Theory TV show.
observer.
They do
Those
some
emitting
explaining
waves
similar to what I
moves.
was trying to accomplish
In the
with this
direction it's
drawing
moving, the
about
wavefronts
how the
bunch
motion
up, and behind
affects
it
the
they
spacing
spread
of the
out.
waves.
If
And then they
and
give
the
us
car drives
some
past you very
examples
fast.
that I
As it
think
does so,
are
it honks its
very
horn
nicely.
because you're standing in the middle of the road.
They're
The honk
very
to
well
you
done.
might sound something
And so
like this.
I think that answering conceptual questions and
So it
just kind of
starts at a high
understanding in
pitch and
general
moves to a
the
lower
real
pitch,
life
even though from the
application
driver's
of
perspective, the
how
horn
the
is
Doppler
playing.
effect works. The visuals that they give here, the animations are really nice. So if you feel like after this lesson you're still a little confused, especially on the conceptual understanding of what happens with Doppler effect, when is it a higher pitch, lower pitch, go back and watch that video. All right, we're going to go ahead and get into the math work that is related with this equation, or with this topic, sorry. So we have an equation here. This is going to allow us to solve for the perceived frequency. So my formula says F equals, and then on the right-hand side, we're going to have an F naught. So this lowercase f is for frequency. And you can see over here, I have a sort of a legend, a little key. The F all by itself is our perceived frequency. So this is what the observer hears. This is most often what we are going to ask you to solve for. The FO that I just put on the screen, This is a subscript O, and it's pronounced not, this should be pronounced F naught, but we are going to say that the O stands for original. I think that's easier for students to remember. So the FO is the original frequency, and so this is going to be the frequency that the sound is actually emitted from the sound source. Then we are going to multiply this by a fraction. In my numerator, I am going to have a V, which represents the velocity of sound, and that is actually going to be present in the denominator as well. We're going to be adding in the numerator, we're going to be subtracting in the denominator. The way that I would like for you to use this equation, these two signs do not change, okay? Then we're going to have VO, and then we're going to have VS. And this is my equation for Doppler effect. Now, let's talk about what these symbols mean. I'm going to write some stuff down in case that is a little easier for you. So the V all by itself could also be written as V sound. And this is going to be the speed of the sound. Now, it's designed to be through air specifically, because we are talking about somebody who is perceiving a sound. So that means somebody's ear is receiving that signal, and so it's traveling through air to get to the ear usually. So this is by default going to be the speed of sound through air. If we are told in the problem that the sound is traveling at 42 meters per second, then 342 would go here, and it would go here. Okay, it would go in both places. It's always going to be the same number, both top and bottom. If they do not give us a value for the speed of sound, then we are going to be using the average speed, which is going to be 340 meters per second, if they do not give us a sound, speed for sound. Okay, then we have our VO and our VS. So VO stands for the velocity of the observer. I did not spell that right, sorry. The velocity of the observer. So sometimes I write this VOBS, just kind of shortening that up. And so this is going to be who hears the sound. This is going to be the living thing that hears the sound. It does not always have to be a person. Sometimes we give you questions about animals and such. So this is a who, okay? It has to be a living thing with ears to hear. The VS stands for V of the source. And so sometimes I write this as a VSRC, again an abbreviation for the word source. And this could be a who, or it could be a what. And I guess a who could also be a what, right? So we're going to say this is what makes the sound. Okay, so the source is the who or the what that creates the sound, and the observer is the who that hears the sound. Okay, now down here we have some more information about velocity either being positive or negative. So remember, velocity is a vector where we have positive and negative values assigned to different directions. So in this particular situation, the direction that the object is moving, that's making the sound, the direction that the observer is moving, that's listening to the sound, is going to affect whether it's a higher or lower pitched frequency that the observer perceives. So we are going to have a positive value for our velocity if the object is moving towards the other object. So that means my observer could be positive or the source could be positive. But notice that my symbol to add in the numerator and subtract in the denominator does not change, okay? The velocity value would be negative if the object is moving away from the other thing. So this observer could have a negative velocity if he is moving away from the sound. The object that creates the sound could have a negative velocity if it is moving away from the observer. So both velocities could either be positive or negative. I expect that you can plug in a velocity that is negative in both cases without any trouble. We can add a negative number or we could subtract a negative number, okay? And so this is how I would like for you to use this equation. So we're going to do an example here, so hopefully this will make a little bit more sense. Barney is a bumblebee and he is flying at 6 meters per second. So we're going to say here's Barney. And he is being chased, so 6 meters per second. He is being chased by Betsy. So here is Betsy, and since they're both the letter B, I will give Betsy a bow because it's a girl. Okay, so Betsy is flying at 4 meters per second. It says Barney's wings beat with a frequency of 90 hertz. So Barney is creating the sound and it has a frequency of 90 hertz. So this is going to be the original, the actual frequency that is emitted by the sound source. What frequency does Betsy hear? So this makes Betsy the observer. And so she is listening for the sound. And so we're going to say what she perceives that sound to be. Okay. Now, Barney is creating the sound. So he is the sound source. Betsy is listening. So she is the observer. Barney is being chased by Betsy. So Barney is trying to get away. Betsy is following him. Towards is positive, away is negative. So Barney is going to have a negative velocity and Betsy is going to have a positive velocity. So if we list this out, our sound source is a negative 6 meters per second with an original frequency of 90 hertz. Our observer is moving towards, so she has a positive 4 meters per second, and we're trying to find her perceived frequency. So my formula says F is equal to F naught times V plus V of the observer divided by V minus V of the source. So there's my equation. So I'm going to plug this in. F equals 90 times, and then I'm going to say, they didn't give me a velocity for the speed of sound, so we're going to use the average of 340 as our default, plus minus. Now, my velocity of the observer goes here, and this could be positive or negative. So here is my observer, and so we're going to put in a positive 4, okay? The velocity of my source goes here, and so here is my source, and once again, this could be positive or negative, and so in this case, it's a negative 6. So I'm going to say 340 plus 4 divided by 340 minus a negative 6. All of that is one fraction that is then multiplied by 90. When I put this in my calculator, I get 89. Oops, sorry about that. I get 89.4797 ... So we are going to have 3 sig figs, so 89.5 hertz. This means that Betsy perceives a lower pitched sound. Barney is moving away from her. That matches the general idea that we were given in our lesson. All right, we're going to do another example here. We have Miss Gonzalez, who is rushing to the hospital at a speed of 30 meters per second. So Miss Gonzalez is on her way to the hospital. A police officer sees her speeding and turns on his siren. The frequency, so this is the actual frequency emitted by the siren, is 800 hertz. If the officer is chasing Miss Gonzalez, so here's the police officer, he's chasing Miss Gonzalez is moving away. So that means Miss Gonzalez's speed is going to be negative, and the police officer's speed is going to be positive, okay? The officer is chasing Gonzalez with a speed of 35 meters per second. So this is going to be a positive 35 for the police officer. And he is creating the sound, so that makes him the source. Miss Gonzalez is going to be the observer, and she's going to have a negative 30 because she's moving away from the police officer. What frequency does she hear? So here's my equation. So we're going to take 800 times 340 plus the observer, which is a negative 30. 340 minus the source, which is a positive 35. Okay? Once again, the velocity itself could be positive or negative in either location. And so all I did was plug in my negative 30 in my numerator. But it's still 340 plus in the numerator, 340 minus in the denominator. Okay? Once we put all of this in our calculator, we get a frequency of 813 point, I think it was 1 something something, sorry, I don't remember the details. So this comes out to be 813 hertz because once again we need 3 sig figs. Okay. This last example that I'm going to work with you is slightly different. So here we have Kenny, who is in his boat, and he is speeding towards a lighthouse. So here's my lighthouse. Kenny is going towards the lighthouse. All right, so Kenny is traveling in his boat at 15 meters per second. So this is going to be a positive 15 because he is towards. The foghorn blows. The foghorn is located in the lighthouse with a frequency of 180 hertz. What frequency does Kenny hear as he moves? Okay, so students sometimes get a little confused by this. They clearly understand that Kenny is moving at 15 meters per second towards the lighthouse. Kenny is the one that is listening. He has the ears to hear, and so he is our observer. But students do not feel like they have everything that they need when they get ready to plug information into this equation. And I need to remind you, in order for the Doppler effect to be an option for our math work here, we have to have two things. We have to have something creating the sound and someone hearing the sound. So if we look at my list of givens, I have only provided information for the velocity of the person that is listening to the sound. I have not provided anything for the object that is making the sound. So the foghorn is a horn that is located inside of the lighthouse. So the lighthouse is my source. What is the speed or velocity of the lighthouse? Well, the lighthouse is a building. It does not move. It is stationary. It has a velocity of 0. So the velocity of my source is 0 meters per second. I don't know why that seems to stump a lot of students. So make sure you understand that you have to account for both objects, and it's okay if one of those is 0. If that object is stationary, then we're going to have a velocity of 0, and that is completely fine, okay? Now, in this question, let's change things up a little bit. Let's say that in the question they told us that the speed of sound through air is 336 meters per second. Let's just use that instead. So if they gave us a velocity for my sound, now we're not going to use the 340 average that we've used before. We're going to use the 336 that they gave us. So my velocity for sound goes here, and it's always the same number in both places. Plus, minus. Okay, so then my observer is going to have a velocity of a positive 15 meters per second, and my source has a velocity of 0. Okay, so when I put this in my calculator, I am going to say 336 plus 15 in my numerator, and then my denominator is going to be 336 minus 0. When I am done calculating this, I get 188.357 dot dot dot. So my frequency rounded to, let's see, this has 3 sig figs because ending zeros are significant with a decimal. This has 4 sig figs for the same reason. So we're going to go with 3 sig figs in our final answer, 188 hertz.